Sorry for the slight delay, but now we're also online. That's great. Good morning. This is the deep dive session. That's kind of the second deep dive session we are having at IETF. Last meeting we had a deep dive session on router architectures, which people gave us a lot of positive feedback about. So we thought we'd do it again. This time we will look into NICs, and we have some people here who usually, or some of them usually come to the IETF. They're from the Linux NetDev community. We will introduce them, yes, and we're really happy to have them here. So my name is Mia Kühlewind.
I'm Jamal Hadi Salim.
Yeah, and we will start. That's the wrong machine. The note well applies here as well. What did you do? That's fine. So the note well applies here as well. This is kind of a side meeting, but we're still at the IETF, so it applies. And that's our today's agenda. We have the user stuff we have to care about, which is mostly now set up. Jamal will now do a quick introduction to scope our day, or our morning meeting here. And then we start the presentation, and we have some time for questions at the end.
Can we solicit a scribe? Somebody is going to take minutes, or come on, volunteer, scribe.
I mean, we have the recording as well.
We have the recording. All right. And the blue sheets?
I will care what we should.
Okay, so when we were scoping this talk, an hour and a half didn't seem to do justice to the content, so we had to limit the scope. We could have a half-day discussion on not a tutorial, but just high-level topics. So what is in scope is we will talk about basic NIC support, how a basic NIC works. We'll proceed to medium range offload from the host stack to the hardware, and slightly more advanced features. We're going to use Linux kernel as a reference point, not necessarily the only operating system that does this. What's out of scope is we're not going to talk about kernel bypass, so no DPDK discussions. We're not going to talk about small CPE devices that use the same APIs in Linux at least, or very large ASICs, multi-terabit ASICs, which may use the same APIs in some vendor ASICs. We're not going to talk about virtualization, offload technologies, SRIOV, VMDQ, and any newer schemes are out of topic. And storage is also out of topic. So this could be another session in the future. Should this session become exciting to the attendees, we could have another session in the future. The relationship to the IETF, if you're implementing protocols, this is very relevant to you. You're running on the host or some middle boxes which end up using NICs. For nodes that perform both host level features or forwarding functions. So NICs can process a lot, accelerate as well, and have a lot of helpers in the hardware for TCP, UDP, QUIC, TLS, IPsec. A lot of the NVO3 is mostly commodity offloading at this point in time. You can accelerate any of the layer 2 to layer N forwarding and filtering. There's a lot of QoS offloading. It's a very condensed session. So what we'll ask is, we'll only allow for clarification questions, and any other questions that you may have will come at the end. I'm going to introduce the presenters. You have a very competent set of folks here. On the left is Tom Hubbard from Intel, Andy Gospodarek from Broadcom, and Simon Harman from Netronome. And I'd like to acknowledge Boris, where's Boris? From Mellanox. These are very competent folks. They know how the implementations work. They understand the hardware very well, so you're in good hands. Having said that, these slides took a lot of community effort from the NetDev community in general, and this is a list of people who, in one way or another, contributed, shaped, opinionated on what should be cut out, what should be kept, how the slides should be structured, etc. And with that, I'm going to hand it over to the first speaker, Tom. Is that mic working? The mic is, can you turn it on?
How's that?
Yeah.
Oh, much better. Okay, so I'm going to present the fundamentals and basic offloads of NICs. So a few definitions might be useful. NIC is a network interface card, sometimes network interface controller. This is the host interface, physical interface to physical network. Host stack is the software that processes packets and does protocol processing in the host. Typically, this is layer 2, layer 3, layer 4 processing. A kernel stack is simply a host stack that runs inside a kernel. And as Jamil mentioned, for the most part, we'll be referencing Linux for that. Offload is when we do something inside the NIC on behalf of the host. So this is work that we move essentially from the host to the NIC for some purpose, work that involves the networking. And acceleration is offload that is done mostly for performance gains. So what is a network interface card? This shows the picture on the left of a card. And most of you should be familiar with these. Whoever's had a PC, for instance, knows how to plug these in. So they go into the system bus. I would point out this particular card is very ancient. Actually, it has a BNC connector, so this is true Ethernet and ISA connectivity. But nevertheless, it's a NIC, and modern-day NICs obviously look a little bit different, but basically perform the same function. So a NIC is the receiver and transmitter of packets to the network, to the physical network. It's the device that does that. And on the right, we have a stack, and you can see that in the protocol stack, the NIC is kind of at the bottom. And on one side, to the outside world, it connects to the physical media. That could be fiber, Cat5, radio. And we use some sort of encoding or framing over that media, Ethernet, Wi-Fi, fiber channel. On the other side of the NIC, it connects into the system via the system bus. So typically today, this is PCIe or USB. In the olden days, like this card, it was ISA. So the way this works is that NICs have queues, typically. They have a transmit queue and a receive queue. And these queues store the packets or indicate the packets for transmit and receive. The queues are composed of a set of descriptors, and the descriptors describe the packet for the NIC. Some of the important things in the descriptors are where the packet is located in host memory, what the length of the packet is, and then some ancillary information that may have involved, for instance, if this was received as a broadcast Ethernet, and other information like that. So in order to transmit, the host stack fills out a transmit descriptor. And most importantly, it writes the information in that for the packet, where the packet is located in its memory, and what the length of the packet is. It puts the transmit descriptor onto a queue. And I should mention it's a producer-consumer type of queue. So it puts the transmit descriptor on the queue, bumps the producer pointer, and then it sends an indication to the NIC, usually through a PCI write, a register write, that there's work to be done. So the NIC wakes up, it processes the transmit queue, and it looks at each of the transmit descriptors, figures out where the packet is in host memory, performs a DMA operation, direct memory access, to pull the packet into its local memory. And then the NIC may perform some offload processing, which we'll talk about in a bit. But eventually, the packet has to be sent on the network So there is a PHY and a SerDes serializer inside the device that takes the packet in its memory, serializes the data, and sends it out to the actual network. Receive is somewhat similar. In the receive path, the host sets up a number of packet buffers where packets will be stored in its memory, and it puts these into the receive queue in the receive descriptors. So again, in each descriptor, there's a memory location, and in this case, maximum length of the packet. When the NIC receives a packet, it deserializes it, puts it in its memory, again, may do some offload processing, but eventually wants to send that to the host. So the way it works is the NIC takes the next receive descriptor available in the queue, gets the host memory location, DMAs the packet into that host memory, sets the length in the receive descriptor, increments the producer pointer or its consumer pointer in the receive queue, and then it interrupts the host, which is typically an actual system interrupt, and the host wakes up and knows there's packets to process in the receive queue, so it actually reads the queue and then can get the packets that have been received and processes them in the stack. So what I just described is kind of fundamental, and that's the basics of the NIC, and these started in approximately the early 90s. Not soon after, some of the basic offloads that I'll talk about in a minute came into being and were developed. And we can track the evolution of NIC since then. So in the mid-2000s, we have data plane accelerations. So these are more advanced features inside the NICs, IPsec offload, for instance, QoS offloads. And more recently, there's a general movement to make these devices programmable. So at each phase of the evolution, you can think of this as more advanced features, more functionality, more capabilities to process protocols and packets. But fundamentally, the operation of the NIC is the same. It's the thing that transmits and receives packets to a network. So we'll talk a lot about offloads today. I want to give a little bit of motivation. One way you can think of offloads is these are just advanced features having to do with the packet processing or protocol processing that happens to be done in the NIC. So there's a few rationales for this. One is we want to free up the host CPU cycles for application work. This makes sense if the NIC can do the functions of networking in a more efficient way. So since it's specialized hardware, that is often the case. For instance, we can compute a checksum more efficiently than doing it in the host CPU. More generally, one of the motivations is to save host resources. So offloads may save not just CPU, but memory, DMA operations, memory movement, number of interrupts. Scaling performance is very important, and offloads help a lot there, particularly in low latency and high throughput. There's also some interesting use cases, particularly in mobile, where we might offload certain operations having to do with protocol processing to a device for the purposes of saving CPU cycles and saving power in particular on the core CPU. So in short, offloads make sense as a cost-benefit trade-off. If the benefits of moving work into the NIC, you can think of it as a coprocessor, exceed the cost, then it makes sense. In practice, this can be an interesting analysis. So we know that CPUs, for instance, are always increasing their capabilities. On the other hand, the network and things we want to do are always getting more complex. So there's always a bit of a trade-off between whether to offload or run on the host CPU. But in general, we found offloads to be pretty useful and probably will continue that trend. In terms of developing offloads and NIC development in general, in the Linux community at least, we kind of enshrined some of the principles in something called less is more. And I want to give three components of this. So first of all, protocol agnostic mechanisms are better than protocol specific. And this is somewhat of a formalism of trying to prevent protocol ossification. But the idea is if we can develop an offload that supports, say, all transport protocols equally versus one that is only works with TCP or plain TCP/IP packets, Generally, the offload that is more general is going to be more applicable and better for the user. In a similar vein, common APIs are better than proprietary APIs. We have a lot of OSs, a lot of NICs. The more common the APIs across those, the easier it is for users to choose different pieces of hardware. This is particularly important in that we want to avoid the concept of vendor lock-in, which is where a vendor, whether purposely or inadvertently, kind of controls the API such that it's really difficult for the user to change the vendors that they're using. The third point is that programmability is good. So I put this in generally in parentheses. One of the aspects of programmability is if we make it completely openly programmable, especially user programmable, and allow users to do whatever they want, users will do whatever they want. That, as we know, leads to some interesting fracturing of the market and can be precarious. So we always want to make sure that if we're going to create an open program environment, how do we develop the ecosystem properly and maintain some semblance of sanity across these and portability? So we can turn and look at some of the basic offloads. I'm going to skip that slide. So we'll talk about 3 basic offloads, and these are kind of the oldest ones. They're very common amongst NICs. Most of these have been around since the 90s at least. Checksum offload, segmentation offload, and multi-queue. Checksum offload is the offload of the venerable TCP UDP transport checksum. So the idea is that we want to offload the computation of the checksum. So the ones complement summation in particular is CPU intensive. If we offload that to the NIC, we get a nice performance gain. As I mentioned, checksum offload is particularly ubiquitous. It would probably be pretty hard to find a NIC on the market today that does not support some form of this. An interesting twist that's a little bit recent is encapsulation. So what we found is that, say, IP and IP encapsulation, or particularly UDP-based encapsulations, actually can have multiple transport protocols per packet that contain their own checksum. So conceptually, it's possible to have 2, 3, 4, 5, or 6 checksums in a single packet, TCP checksum, a UDP checksum, a GRE checksum. It's all possible. So we want to offload all of those checksums, and we found some techniques that can leverage rudimentary checksum offload of one checksum to actually support multiple checksum even in the same packet. So a little bit of detail. So transmit checksum offload has 2 forms. One is protocol specific, one is protocol agnostic. The protocol specific one, the host sends a packet into the device. The device actually parses the packet, determines if there's a transport header and a checksum, and if there is, it does all the operations to set the checksum. So to perform the ones complement checksum over the data, it will compute the pseudo header checksum if there's one there, and it will set the checksum in the appropriate field of the transport layer. The more generic method is for the host to indicate in instructions exactly how to do the checksum. So it provides 2 pieces of information to the device. One is where the checksum starts, so the starting offset in the packet, and the other one is the offset to write the checksum, which would typically be the checksum field of TCP, for instance, and then the start would be the offset of the TCP header. The device gets this, and it will perform the ones complement sum starting from the starting point to the end of the packet, and that sum, whatever it gets, it basically adds it in to the existing value in the checksum field and sets the field. As long as the host set this up and initialize the checksum field correctly, the device will set this correct checksum. It has no idea what kind of checksum it is. It doesn't know if it's UDP or TCP. It doesn't care. It just knows it's the standard internet packet checksum. For receive, we have an analogous situation. There is a protocol generic and a protocol specific method. The protocol specific method is called checksum unnecessary. As packets are received, the NIC parses the packet, determines if there is a transport protocol that contains a checksum, and performs the work to actually verify the checksum. So it does a one's complement checksum, computes the pseudo header, adds them, checks if the result is checksum 0. If it is, the checksum has been verified and sets a bit in the receive descriptor to inform the host that it's verified the checksum. So again, that is protocol specific. It only really works with TCP and UDP packets that the device explicitly parses. The more generic method is checksum complete. In this case, the device performs a one's complement sum of the whole packet, starting from the IP header through the end of the packet, and it simply returns that sum in the receive descriptor to the host. The host can take that and actually use it through simple manipulations of checksum to verify any number of checksums in the packet. So this is really efficient, really very generic, and is able, as I said, to verify many checksums in a packet. So looking at segmentation offload, one of the observations that we've made is that networking stacks are more efficient when they process large packets as opposed to small packets. So in particular, per packet processing, per packet overhead in the stack is significant more than processing the data bytes usually. So we want to see if we can arrange the system so we can process large packets instead of small packets. So there's two forms of this. There's one on transmit and one on receive. On transmit segmentation offload, the idea is the host produces a large packet, say a 64K TCP segment, and we want to break this packet up into smaller chunks for sending out into the network, which may have, say, a 1500 byte MTU. So we want to do this as low as possible. So the idea is the stack processes the big packet, processes one IP header, one TCP header, and at the lowest point possible, either in the software or even in the network device, there's a type of segmentation or fragmentation. So we slice up the data, give each packet its own IP header, own TCP header, and send each one. So there is a software variant and hardware variant of this. Software variant is called GSO, Generic Segmentation Offload. The hardware variant is LSO, Large Segmentation Offload. You might see it also called TSO, TCP Segmentation Offload, when this is specific to TCP. Receive segmentation offload is the opposite. So when small packets are received, we try to coalesce these into larger segments and larger packets. So again, this is per flow. Similar operation, and there are two variants of this. One is the software, one is the hardware. The software is generic receive offload, GRO. The hardware is LRO, large receive offload. This particular offload, of all the checks or all the basic offloads, is probably the hardest one. It does require the network device to be able to parse the packet and understand a lot of details of the protocol. So for instance, the implementations that do this really only understand TCP usually, some of that encapsulation. But until we have, say, a fully programmable environment, it is hard to generalize this one. One thing I'd like to mention about segmentation offload, this really only works in conjunction with checksum offload. So this is a good example of where we develop a more complex offload, but it requires some of the basic offloads in order to operate. And we'll definitely see this with some of the more advanced offloads that we'll talk about in a little bit. The third basic offload is multi-queue. This is done in conjunction with multiprocessor systems, and the idea is that the NIC has some number of receive queues and some number of transmit queues, where queues usually are assigned to a CPU, and we get a sort of parallelism by the CPU to queue affinity. One of the interesting properties is that once we have queues, we can assign properties to them. Particularly in transmit, each queue can have its own attributes. So for instance, we can have high priority queues and low priority queues. One of the important aspects when we deal with multi-queue, we do want to try to keep packets in order. So for instance, we don't want to be distributing packets in the same flow across different queues, either in transmit or receive. So there are some techniques in the model of queuing to try to enable the in-order delivery as much as possible. So on transmit, there are essentially two methods to do this. One is the easy method, which is fundamentally each CPU is assigned to a queue. So when an application is sending a packet, for instance, the queue chosen is the one associated with that CPU the application's running on. And the advantage of this is that we get this sort of siloing locality. For instance, when a packet is sent on a queue, we have to lock the queue in order to manipulate the queue pointer. If we do this in CPU per queue, then there's no contention for the lock and no contention for the structures of the queue. The second method is when the driver selects the queue. So as I mentioned, queues can have some rich semantics, such as priority. What we've done there, instead of trying to expose all possible combinations of this, we allow the driver to basically understand the queue layout, the topology, what the different queues are. And when the host stack wants to send, it basically asks the driver that has intimate detail of the device, what's the best queue to send this on? And the driver can do that. So for instance, if we're sending a high priority packet where the metadata associated with the packet said this high priority, when this goes into the driver, it looks up the queue that's appropriate for that. So they may have a CPU to queue affinity, priority. There's also other attributes you could apply, like rate limiting. On the receive side, this is normally called packet steering. So the idea is when packets come in to the NIC, they need to be distributed amongst the queues. It turns out this is a lot like ECMP, and some of the techniques are very similar, where we're trying to distribute in ECMP to multiple interfaces. On the stateless side, there are two forms of this. One is called receive packet steering. That's a software variant. RSS, receive side scaling, is a hardware variant. They both essentially work the same. When packets come in, a hash is performed over the 5-tuple of the packet if the transport layer is available, or 3-tuple if we're using the flow label. But the effect is to identify the flow by a hash, take that hash and map that into one of the queues. And that way we're also consistent. So for this particular flow, it always has the same hash, therefore we can always map that to the same queue in order to facilitate in-order delivery. An extension of this is something called receive flow steering. In this case, the host itself can actually sort of program for each flow which queue to use. This is a very powerful mechanism. So on a per flow basis, the host can indicate, okay, for this flow, use this queue. There are two variants of this also. There is a software variant and hardware variant. The advantage of this is to get a really good isolation. Some people use this where they pin an application to a CPU, where that application only runs on that CPU, and they associate a network queue with that application, and receive flow steering can actually arrange it so that packets only for that application's flows go to that queue. So it's very siloed. The application acts like it's the only application on the system. We get a lot of performance gains that way. So with that, I will turn it over to Simon, who will talk about some of the more advanced offloads.
Thanks, Tom. So far, Tom has taken us through some basic offloads and the basic functionality of the NIC itself. Well, as the use cases, the demands of the users evolve and the hardware evolves at the same time, it only makes sense that more and more processing could be pushed down to the hardware. And so in this section, we'll look at examples of that in terms of offloading more of the data plane, more of the packet processing. But before I get into some examples in that area, I'd just like to quickly cover some of the hardware solutions that might be used in this kind of area. So it's important to note that these solutions, it's a little bit of a mix and match. It depends very much on the use case, which choice is appropriate, and some hardware choices match some use cases more naturally than others. But at the same time, they're not necessarily mutually exclusive. So far, the NICs we've talked about fall in the first category, where you have a fixed data plane. And so this will become kind of ASIC that implements a pipeline in hardware. And we can also use more programmable technologies, and these kind of fall into three subcategories. We have semi-specialized processors called network flow processor, or NPU, network processing unit. And so in this, it's a little bit similar to a general purpose processor, like a CPU on in a server. You have instructions, it executes a program, and that program describes the pipeline. They differ from a general purpose CPU is that they are a little bit more specialized, so they might have instructions to do network-related functionality, or they might have much higher thread density, things along these lines to make them more suited to network processing. And then you have the FPGA, which is probably the most programmable solution possible. Here we have gate-level programming, so essentially you can program the hardware itself. And so you can describe at the gate level what the pipeline should be. And then we have general purpose processors, so this would be putting, say, an ARM processor onto the NIC to execute the pipeline. And Andy will get back to this, the programmability aspects a little later in the presentation. So back to data plane acceleration. Here we have a diagram that represents roughly how this works. So we have applications, and then in the kernel we have an implementation of a data path. And then down in the offload NIC we have a data plane, which implements some or maybe all of the functionality of the data path in the kernel. And so this is able to forward, for example, forward packets around and so on. So the advantage of this is that more and more of the processing of the packets can be done in the hardware, and this alleviates the host of this task, so the CPU can be used for other things. It also can lead to higher performance depending on the use case. So here we're going to go through 4 topics in data plane acceleration before we move on. So the first one is match action. So this is a foundational building block of a data path, and indeed of offloading a data path into the NIC. So the first step is that we do some kind of header extraction. So we pull out some fields, for example, the 5 tuple. But we also have metadata, for example, the port that the packet arrived in. Other things can also be available. Then using this data, we typically do a hash. And then the hash, looking up in the hash table, we try to find a match. And if we do find a match, then the match will supply some kind of action that should be executed, or a list of actions even. And so this could be to forward to a different port, it could be to drop, it could be to move on to another table, if you have multiple tables present. It could be to do some kind of modification of the packet. We can also do more stateful things, like we can do policing, which I'll get to a little bit later, or connection tracking. So using this max action scheme, we can create a forwarding pipeline. And so here we have the matches and actions, which we can use to forward between physical ports. The header extraction can operate at various levels of the protocol stack. So you would begin with L2. You can also extract the source and destination IP addresses from L3. And then you can also select, for example, the ports at layer 4. So you can create a specific rule, for example, do some kind of special treatment on port 80 traffic, possibly to a separate host. It's fairly flexible in this regard. Oftentimes, this is set up in such a way that if the offload data plane can't process a particular packet for some reason, perhaps it's for a protocol that it can't understand, perhaps its table capacity has been exceeded, or any one of a variety of reasons. You may have a mechanism in place that allows the processing of the packet to be pushed back to the host. And the host may react to that in various ways. It might process the packet, and then also program the hardware to tell it what to do the next time it sees a packet, say, for the same flow. And we can also do tunnel encapsulation and decapsulation, as well as tagging at this point. This is, of course, optional, depending on what the desires of the system are. And so in this system, we can see that essentially we have a packet processing pipeline. Packets can come into the machine, they can be processed, they can be encapsulated or decapsulated, and they can be pushed back out of the machine or towards the host. So building on this a little further, we can also implement QoS in the NIC, or offload the QoS in the offload NIC. So in the ingress case, this is packets that are arriving on the machine. The interesting thing about this use case is that there's no queue available. So the actions that can be applied are fairly limited. We can police the packet, perhaps by dropping it or marking it. We can filter it, and so on. Egress is a little bit more interesting, or a little bit more complex, perhaps is a better way to put it, because we have a queue. So we have the option of doing a much larger number of different things with the packets in order to, for example, enforce a desired packet rate. We can delay packets. We can, of course, drop them, and so on. And this is an area which has received significant research over the years, and most of this research is applicable. There are, of course, challenges in implementing individual algorithms on an offload NIC as opposed to a host. It's usually a more limited execution environment. But nonetheless, the same principles generally apply. Now, in this diagram, we have packets coming into the machine, into the NIC, and also exiting the NIC. So they're being forwarded from one port to another of the NIC. That could be a virtual port or a physical port. And the NIC is applying some kind of QoS as they traverse the NIC. In the next slide, we have a slightly different setup. So here we have packets, of course it's two-directional, but we'll only talk about one direction, which is packets originating from an application running on the host and heading out towards the wire, out a physical port of the NIC. And the NIC is applying some kind of QoS policy to those packets as they traverse the NIC. So in this particular case, we have different applications, and by some kind of selection mechanism, they are allocated to different queues, and each queue has a different red instance running on it, and this could mark the packets or drop the packets if they're exceeding a certain rate, and so on. And this, of course, is not limited to red. I just use this particular example. So the point I wanted to draw out here is that there are two fundamentally different models here. One is of applying QoS between ports of the NIC, and one is QoS applied to packets originating from the host and then passing through the NIC. So moving on to the last part of my section, I'll talk about crypto offload a little bit. So this is a little bit different to what I've talked about so far with the data plane processing packets, in the sense that what we're really focusing now is offloading from the host a very computationally expensive part of packet forwarding if you are applying crypto. And crypto itself tends to be quite complex. So what we have at the moment is we have an offload of TLS, and this is only dealing with TLS connections which are in the established state. So the host is still responsible for the connection establishment. It's still responsible for the TLS handshake, the certificate negotiation, and so on. And once a connection is established, then it is able to pass that connection to the KTLS module inside the kernel, which in turn, so at that point it's passing the credentials of the connection into the KTLS module, which in turn can push those same credentials and connection information down to the hardware. And then when we do transmit, essentially what the host will do is to form up a TLS frame, but it does not perform the cryptographic operation. So the authorization hash, there's space for it, but it's not filled in. And the packet or the record payload is in plain text. And then the offload NIC will receive this record and perform the cryptographic operation. So it turns the plain text into ciphertext, and it fills in the hash. On RX, things are reversed. However, it's worth noticing that RX is significantly more complex implementation-wise than TX, because one needs to deal with things like out-of-order packets, reassembly of fragments, and so on. Essentially, you have much less control of what's coming into the box as opposed to what's going out of the box. IPsec acceleration follows a similar principle to the TLS, in the sense that some parts are offloaded and some parts are not. And at this time we have two models for this. One is the crypto offload, which is very similar to what I described to TLS, in the sense that it is the host's responsibility to add the IPsec headers to the packet. But it does not perform the cryptographic operations, which are left to the card. It's worth noticing at this point that, on the one hand, this combines a number of different offloads, which we've already discussed. The LSO, the segmentation offload, and the checksum offload. So if one is offloading the crypto, one also needs to offload those operations. But conversely, with IPsec traffic, one cannot offload the segmentation offload or the checksum offload if one does not also offload the cryptographic. So there's significant benefits to being able to build this stack, but in a sense it's an evolution where one could not build this particular piece of technology without other pieces that have come earlier, the ones that Tom spoke about. The other model we have is a full offload. So by full offload, what we mean here is that the hardware is responsible for adding the IPsec headers on transmit, and of course removing them on receive. This can lead to additional savings in host resources. It is clearly also more complicated to implement in the hardware. And regardless of which of these two models you use, the key negotiation between the endpoints, which itself is quite complex, remains on the host. There is scope to offload this, but the way that these things tend to evolve is that you start with something simple that has a very large benefit, so the crypto offload, and then we move to a fuller offload, and potentially the IKE could also be offloaded at some point in the future. So with that, I'd like to hand over to Andy, who will now address further evolutions in NIC technology. Thank you.
All right, so you've already heard a pretty long discussion about how these things all work, so that's good. I appreciate everyone who's still awake and has finished checking all their email. Now we'll talk a little bit about programmability. So, what Simon and Tom talked about are really all these offload features that were enabled exclusively by hardware providers or hardware vendors who feel like this is something useful, probably from feedback based on users. Maybe not, it sort of depends. But we're gonna build on that and talk about how sort of the next evolution in this path is fully programmable NICs. So as Tom talked about, those could be good, probably good, but really there's a couple key features I want to highlight and think about, and why programmability of a NIC would matter. So right out of the gate, I think one of the really important things is that it facilitates really a rapid protocol development. So we're kind of in a phase right now where fixed function offload is so powerful and so useful that if you want to deploy a new protocol, or you think you want to help develop a new protocol and you want to rapidly iterate that, one of the problems you find you're getting yourself into is that, well, are we going to really cripple our current infrastructure are really going to burn more cores processing packets just to support this new protocol? What if we just live with the old one and deal with that? So programmability gives you that option to offload those operations to hardware and really still give you the efficiency you want in the new protocols. So the other obvious one is to quickly fix bugs and security problems. No one in the Linux community likes to remember 15 years ago when anytime you had somebody report a problem with some TCP-related thing on Linux, one of the first suggestions on a mailing list or on a message board post was, oh, did you try turning off TSO? Because it was sort of famously, it was problematic for some NICs or some kernels at some point. And, you know, that became, that would be something that if you had a programmable NIC and you knew what the problem was, because probably you wrote it, you could go fix it. So additionally, rolling out new security fixes, always a great idea. There is this notion, right, that if you run a large or small scale data center, there is going to be some magic packet that's going to melt your network. And this would give you that opportunity to snuff that out in hardware before it gets too far. So today in the programmable NIC world, there's really two sort of main types. One is special purpose hardware, FPGA, NPUs, that Simon has referenced before. So this is something that we're going to program, very specific hardware we're going to write code for. And then the other one is really a new class of NICs that have appeared in the last couple years that really just contain a general purpose processor. So this might be an ARM, an x86, a MIPS, maybe in the future like RISC-V, but really just something general purpose that can run any code. So, and I think really, while this might seem today like something that isn't exactly what you might want, I sort of looked at some of the forwarding plane realities slides from the last IETF, and I think there's a really interesting quote at the conclusion at the end of that what's niche today can be broad tomorrow. And I think that's generally speaking what we've seen across the board in networking and in NICs, that there'll be someone that'll roll out a new feature and someone will think, I don't know, before long everybody's got it and everybody wants it. So I think programmability is going to be that next piece. So kind of build on the common language that we had for our pictures earlier. Hopefully this language resonates with people, otherwise it's a bummer because we used it in the whole deck. So we really do in this case, when you have an FPGA or an NPU, the control plane is still going to stay in your host kernel. So it's going to do, if you're running a routing daemon or something else that's setting up flows, all that still runs there. But now we're in a case where this offload data plane is going to run down in the FPGA or the NPU. And in fact, one of the unique pieces with this is there will be cases where a software data path does not exist in the kernel for whatever feature you're adding. Now that's a little bit different from what we do in the Linux community, where if there's hardware offload capabilities that are there in your hardware, there's sort of an insistence that there's a software fallback data path that exists. And within Linux, that's been extremely helpful, and we're going to continue, I think, to push that. But this is a case where that might not be the case. You may just have a data path that's completely done in the kernel with no software fallback, at your own risk, I guess. And in fact, that data plane could be expressed in a variety of languages. So, maybe P4, eBPF, NPL, or maybe just a native instruction set for that NPU. As Simon talked about, many NPUs have something that maybe have special instructions for performing operations. And the key that we talked about too is that this is dynamically programmed. So in this, this death packet that could exist, you can roll out new code quickly. Or if you're rapidly developing a new protocol and you start to say, you know what, maybe I don't need 350 bytes of header to describe this new protocol. Maybe we'll make it a little shorter, like 324 or something. Who knows? So the other piece is really a general purpose processor. And so this is a little bit of a unique situation, a little different than we've had in the past, but it's becoming pretty popular. And so this is a case where we're moving the entire host networking stack down onto the NIC. So, and yes, I said that right. So what that actually means is your NIC could actually run another copy of an operating system. Some people shudder at this thought because maybe it sounds a little more complex. But the fact is, if you have this already implemented in software on your server, you could actually move it down to your NIC and free up those server cores from doing that work. So in this case, the data plane offload is down on this general purpose processor, as I mentioned. and also the control plane. So now, what if your routing daemon was running on the NIC, or what if your whatever was receiving, open flow messages from a controller was running completely on the NIC. So now you found yourself consuming 0 host resources, server host, not NIC host, sort of different CPU complexes there, or not sort of, actually different CPU complexes. So now you're not consuming any of the resources of your server, and you can free them up for doing useful things, whatever those may be. So this control plane offload is also really nice if you have what some are calling now a bare metal deployment, where you're setting up servers. You don't know exactly what they're going to be used for, but you're responsible for networking. You can feel pretty confident that there's a good chance that your server administrators are not going to ruin whatever network setup you want them to have. Pretty confident. Also, in the multi-tenant deployments, this would be really good. You can make sure that no one person has a chance to destroy too much. And really, it brings a lot of the server networking administration back into the purview of the network admin. I think that's sort of a constant struggle between those two groups, somewhat understandably. So this gives networking's tentacles to get a little bit further into the server, if you will. So kind of in the same vein, here's that picture again. So now we've got this general purpose processor running down on our programmable NIC, running whatever OS you want. And this forwarding functionality, again, moves completely away from the server cores down to the NIC. So this would mean that, obviously, if you have applications that are running in your server, they're still going to get the data that they need, but you're not spending your time just needlessly moving packets between different applications, whatever those look like. And the reality, too, here, and it doesn't get any more recursive than this, I promise, is that the programmable NICs also have offload-capable devices. These things are all being put on the same die, so you'll have a control and a data plane and a fixed function device that's all embedded down. But like I said, I promise that offloaded data path on the fixed function device doesn't also contain another general purpose processor and another one on down. It's just a simple, I appreciate that. It's just a simple, the simple fact is we're building these chips that are pretty large and have both the general purpose, maybe ARM or MIPS cores on the side with a fixed function ASIC. But there are also people building NICs that, in addition to that, have FPGAs or NPUs as well. So I think this is kind of a new world in a lot of ways. I think there's not a large number of users that are doing this, but I think this is a strong case, especially in a place like this where we're seeing rapid protocol development, where the programmable NIC is an extremely powerful option and extremely interesting going forward. So I think really the way I want to summarize this is that we think about the networking trends going forward. There's an insatiable need for more bandwidth and lower latency. I think the devices that we carry around in our pockets every day that help us consume more and more data in not only in the air, but where the actual wires are in the data centers, there's just, people want more all the time. I'm amazed at how many people are walking around doing video calls or driving doing video calls. I wish that was a joke, but it's not. And I wish it was passengers. But anyway, and I think we're seeing more and more, too, that there's an interest in deploying new protocols. I regularly hear requests for things that, we wonder how we can make the hardware that is fixed function support and how long it will take to maybe support that. So this gives a new option for people that want to do those things quickly. And I think that the NICs are going to work together with host operating systems to make these things happen. We don't see offloads going away. We see offloads becoming more powerful and becoming more flexible and continue to be important. So, and I also think that the programmability and this flexibility will really spur innovation that we haven't thought of before. I think that's the magical part about some of these devices that are completely, or not completely, fairly flexible, is you get the chance to do something that you would have never thought possible a few years ago, and who knows exactly what will come next. So I think that's, to me, really exciting. I think that's it.
Yeah, thanks. Let's give him a hand, please. Okay, we don't have much time left, so, but we'll open the mics now for anybody who wants to go up and ask. It's a discussion. Please use the mic, state your name, and it's being recorded. And who hasn't signed the blue sheets? Everybody, if you haven't signed the blue sheets, please sign.
David, we start over here.
David Black, first of all, many thanks for consistently using the Linux example throughout the talks. Everybody's on the same page. You may not be able to answer this question, I'm going to ask it anyway. Can you say anything about significant differences in other important operating system environments?
You can use the mic from there. You can use the mic. Okay.
I'm being told to sit down here and share the mic, so. I think everyone wants to answer this one. So I think the question was about whether or not we see consistency across other operating systems. Is that right?
The question in particular was, can you say anything about how you've described things work in Linux differ significantly in non-Linux operating systems?
I honestly don't have a ton of visibility in that. Tom, it looks like, okay.
So to answer the question, I would point out that some of the earlier work actually came out of Windows. For instance, RSS was literally invented. I think it was NDIS described that. And I believe they had the early checksum offload. And I think what happened is, as Linux became kind of more popular and open source, we had a lot of developers that are working on that. And at some point, the NIC vendors, as the volumes go up, they start to pay attention. That being said, we do know that FreeBSD may use some of these. I know that some of the work that we did in the packet steering was being applied. And that's a good thing. So like I said in my talk, we do want common APIs across OSs. But most importantly, I don't think there's anything we're doing in the NIC that would be specific to Linux or any particular OS. In fact, I think some of these techniques would even be applied in something like DPDK or kernel bypass. So again, we're just using Linux as a reference. Obviously, major vendors support Linux, FreeBSD, Windows, and DPDK. And the more features we can have common across those, the better, obviously. And it's good for us if if the features are common, because then we have common support and things like that.
Yeah,
Bob?
next.
Yeah. Okay. Bob Briscoe, independent in this sense. You've talked a lot about different features on different cards and all the rest of it. When you're writing the code, you've got to know what the card can do that's on the machine that your code happens to be running on. So I don't want you to sort of explain all about the APIs now, but really the question's more about from what I've seen is going on. Essentially, it's someone writes a page to say, what's the consensus on what people do, say for offload, and does that need standardization? Is it working at the moment? Just having it done ad hoc, would it screw it up if it was standardized? I'm just thinking it seems to be all very ad hoc at the moment. How the description of what the hardware is capable of, so that you can write a code to know what to use.
Yeah, so I think, I don't know that, it might feel a little bit ad hoc. I feel like there's a fair amount of communication within the kernel development community as if to communicate up to the upper layer stacks what's available. And we have lots of feature flags and feature capabilities that are enumerated. I think part of what's done at some of the different conferences throughout the year, whether it be NetDev or Linux Plumbers or others, is to help get people together and come up with some of those. And I think as we've started with basic offloads, whether it was checksum or TSO or things like that, and we've gotten beyond doing things like flow offload, that's been negotiated, so to speak, fairly well. It does feel a little bit ad hoc, though, especially I think from the outside, because what probably, I don't know if outside's the wrong word to use. As an observer, it probably might feel ad hoc because you just see patches show up and support exist, And usually what happens is one vendor will come up with it, another one will say, oh yeah, me too. And then they'll do it and maybe enhance it a little bit more. But I think that's the goal is to have, write the code once that's your application and have it run across multiple vendors. Yeah. And I think we do a really good job of that right now.
Okay, so basically your answer is the process isn't broken, it just looks like it is from the outside.
That's probably fair, yeah.
Lorenzo Cooley, Google. I had a clarification question for Tom. I think, did I hear correctly that you said that implementing any sort of receive offloads requires checksum offload? And if so, why? Or did I misinterpret what you said?
The implementation for checksum offload, what was the specific
No, the question, I think you said, and I may be mistaken, that implementing anything like GRO or LRO requires checksum offload, otherwise
Yes.
it doesn't work. I just wanted to know why that is, because I don't know.
Well, so if you think about, let's look at large segmentation offload. So in the NIC, this is splitting a packet up into individual TCP segments. Each TCP header has its own checksum. So I need to actually, after I do the segmentation, then I need to set the checksum. It has to be per packet. And this is actually one of the trickier things with something like segmentation offload. The fewer things I have to do per packet, the better. If it's the case where I could just copy all of the headers to each segment, that's a lot easier. But each time we have to consider, like IP ID is another good example in the IP header, but packet lengths are always interesting, and checksum's the hardest one. So anytime I have to set something that is unique for that packet, I have to do that in the NIC, and checksum offload is definitely one of those. So this is a case where we kind of lose the ability to make it completely generic, although there are other avenues. But at some level, we have to have the NIC have a way to understand how to dice up packets.
And for receive, you have to do it because you have to check the individual checksums, otherwise you might end up returning a corrupt bigger packet to the stack.
In terms of capabilities, you mean?
No, for receive, you also need checksum offload for the receive offload. Yeah. Okay. The other question I had was, is there somewhere? I mean, so the earlier question sort of essentially said there's a cabal of 10 people in the world who actually know how to do this. Is there any sort of documentation where we can point vendors to say, hey, please implement checksum offload, and here's how to do it? Because there exist cards that don't do it today, not PCIe cards, but.
I think that goes back to kind of the ad hoc nature of it.
So that's a no then.
Okay. I mean, do you want it to be super formal or informal? I think when we're shooting for programmability, that will actually solve a lot of that, such that you can add different protocols on the fly with different characteristics.
Thanks.
We quickly take a question from Java, actually. So there's a question from Michael Aberson about PassMTU. He's asking, when doing hardware offload, does it matter does it matter much to the host OS if there's lower or higher MTU on the wire? And with GRO, it seems it shouldn't matter. Yeah, sorry.
Regarding PassMTU, doing hardware offload, does it matter as much to the host OS is lower or higher MTU? So the question was about PathMTU and I suppose segmentation offload. So it does matter, and in fact, when we're doing something like LSO, TSO, we aren't just chunking up packets per the MTU. We want to abide by the PathMTU. So the way it works is the host stack actually tells what the size is of the packets to go out, so we can abide by the PathMTU. One of the interesting things that we try to do is when we're sending LSO, try to keep the packets the same size except for the last one. That simplifies the problem that we just talked about with Lorenzo, where we have to set the length for each packet. Easiest way to do that is to kind of infer what the lengths are. So we tell the NIC, this is the length, the maximum length. Make all the packets the same size except for the last one, which could be short. And then that way we accommodate path MTU. So in terms of larger MTUs in the data center, we're seeing like 9K MTUs with jumbo frames. That's actually a little less pertinent to LRO and LSO. In that case, we're actually just using the native MTU to accomplish the larger packet size. So in some circumstances, that's a little less important if we already have a large MTU or path MTU to begin with.
Roland Freisig in Ant Labs. I was wondering about the crypto offloading that was sort of in the middle of the presentation. That sounds very interesting, but what I'm wondering about is, to what extent does that sort of repeat the risks of all of these vulnerabilities, such as I think padding oracles and all of that, and repeat that in the NIC implementations? Is there any information about that? Are there experiences with that? All of the stuff that got solved in crypto stacks that are just on the normal CPU?
Was the question portability in the NIC?
No, the question is, I mean, there are all these vulnerabilities if you do crypto implementations, like timing attacks, things like padding oracles, specific to symmetric implementations. To what extent are these, what is the risk that these get repeated in the NIC implementations? And if they are in your NIC, how do you fix that?
Yeah, so as I understand the question is, if we look at crypto, there's a wide variety of attack vectors, varying complexity. And any individual implementation might be suffering from any number of these. So if we push an crypto implementation down to the hardware, what kind of problems might we see there in this area? Yeah, so I think that that's a good point, and certainly we can't pretend that there is not going to be any problems. I think that as the complexity of what you're as the complexity of what's being offloaded increases, so for example, if we move from a crypto-only offload towards a fuller offload, then the surface for these kind of problems must surely exist in my mind. I'm not really sure what the best way to move forwards on this. Certainly the vendors or the suppliers of the code, or ideally open code, would need to move rapidly, but perhaps we also need to have some kind of mitigations in the system. So I don't know if they would be relevant to something like a timing attack, but if it was, say, a packet of death type of attack, you may have a facility in the system to allow the user to maybe using some programmable component or something to mitigate against that.
Right. But I mean, would it be a matter of flashing the NIC and putting new software in to fix something like that, or is it you can throw away your NIC if the vulnerability is serious enough?
So I didn't quite catch that, but I guess the question is, what would be the mechanism to fix it? And I think it would depend on the implementation. I mean, if it's a kind of a fixed device and you're receiving firmware from the vendor, then I suppose the main avenue other than mitigations would be to get an updated firmware. Okay. But as we move to a more programmable world, that the users should have more flexibility to address these problems themselves. Okay. So to react more fluidly to the situation.
Thank you.
So the next session starts at 10. So we could have like a very, very quick question, or we take this offline.
Okay, wait a minute. It's a simple question.
Okay, quick.
What we see exactly? What we see is that there is a trend towards moving protocol implementations to the application space for various reasons, and we see that with Quick in particular. What I've seen in your presentation is that the interfaces that are shown are through the kernel at a system level. Is there work to enable APIs that can be used directly from the applications to use the offload functions?
I think within the Linux kernel there is a little bit of that. There is actually, there was a presentation done last year in Prague at the NetDev conference about actually offloading quick and what could be done, what kind of kernel interfaces are needed in order to make that possible. So I think that I think the move to protocol implementations like that in user space is maybe a result of hardware inflexibility.
Well, you could say that, but the move to user space is also the idea that it's developed independently of what the kernel does. So
actually, Christian, I have to ask you to take it offline because that could be a whole another session to talk about that, right?
that was a simple question.
Yeah. No, I think you're still here for the rest of the day, all three of you, right? Yes. So people can approach you with more questions. Thank you, everybody. I hope you enjoyed it.
Thank you.
And see you next time.